Okay, so yesterday we talked about Newton's second law of motion, in which Newton defines the relationship between force, mass, and acceleration. Acceleration equals force over mass. So the ratio of the force applied to the mass that it's applied to determines how much the motion is going to change. Okay, and we know from that and from Newton's first law of motion that in order to get that acceleration, to get that change of motion, we have to uh, apply an unbalanced force to it. The bigger the force for the mass, the more the acceleration. The bigger the mass for a certain amount of force, the less the acceleration will be. That relates to inertia. Well, we've also been talking about gravity. We did the force of gravity lab, where we determined that the gravitational field strength here on Earth is 9.8 newtons for every kilogram. And we also looked at how that value actually determines the rate of acceleration for when gravity pulls down on things, which is 9.8 meters per second squared, or meters per second per second. Let's say we're going to be focused in on gravity all on its own. So gravity is an inescapable fact. We've been talking about that. Gravity is going to pull you down no matter what happens. As long as you're on the planet, you cannot ignore the notion that there is this attraction between you and the planet. Again, law of gravity. Any two objects that have mass exert an attractive force on each other. Okay. One way in which we experience gravity is as weight. Weight is defined as the force of gravity acting upon an object. When you use a bathroom scale to measure your weight, you are actually looking at the force of gravity that is pulling you down. So when you stand on that bathroom scale, you get pulled down and you squish the scale, and then there's the normal force that pushes back up, and those two forces are balanced, and that's how your bathroom scale determines what your weight is. Now, we measure weight in pounds. The SI unit for that is newtons, but pounds and newtons both measure gravity or force. Okay, gravity is a force, so any force. Now, weight, because it's the force of gravity, is not the same as mass. During class, when we talk about measuring the mass of things, if people say weight, I always correct them on that, because we don't use triple beam balances to weigh things. We don't use electronic balances to weigh things. We use those devices to measure mass. Okay, mass, to review from earlier this year when we talked about our chemistry topics, mass is the amount of matter in the object. Okay, because it's the amount of matter, mass is unaffected by gravity. The amount of matter that makes up something is the same on Earth as it would be on the moon or some other planet. So all of the matter that makes you up is the same in all those locations. But the force of gravity acting on you here versus the moon versus the planet Jupiter, Mars, you name it, that could be different because weight is the force of gravity. To measure the force of gravity that acts upon an object, we must first review Newton's second law of motion. Here we have one of our variations on the second law equation. Force equals mass times acceleration. Okay, sorry, I had to stop there for a second, which to you probably seems like no time at all, but I had to pause. Something happened there. So anyways, Newton's second law equation, force equals mass times acceleration. This is just one of the variants that we looked at yesterday. Remember, always happens. We got the acceleration is also equal to force over mass. Okay. So, as we talked yesterday about things falling and being pulled down towards the ground, the gravitational field force is equal for all things. The amount of gravitational pull per kilogram of mass is the same for all things. We can then equate that to the gravitational acceleration, which in hours 3 and 4 we looked at, and we can talk about in first hour next time I have class with you guys on Friday. Anyway, so know the force of gravity acting upon us, we must know the object's mass and by how much gravity accelerates those objects. So I'm not here to do the object demo, the object drop demo for you. So along with this video in Edmodo, I also linked to an episode of Veritasium. It's about 3 minutes. At this point, I would like you to pause this video and then watch the Veritasium video, where he talks about the acceleration of things being dropped towards the Earth. So pause the video now. After you watch that video, come back. Okay, so you should have watched that Veritasium video. And in that Veritasium video, he does the demonstration that shows that objects fall at the same rate. Now, there's more to the video than that. We'll get to the other stuff that he talked about in terms of the inertia and the forces. We'll come to that here in a little bit. The important thing is that you understand that because of the differences in weight and the inertia of those objects, it's the reason why things can fall at the same rate. And as we see in that video, drop two objects, very different masses, they hit the ground at the same time because they accelerate at the same rate, which is 9.8 meters per second squared. So those two objects are changing their motions the same amount. It takes different forces. Again, we'll come back to that in a little bit. But as we talked about Newton's second law, a greater mass needs more force if you want it to accelerate at the same rate as something with less mass. So gravity, having the same gravitational field strength, will pull on a heavier object with more force, and both things will accelerate at the same rate. You can see that in the video. Now that's for Earth. As we can see here, Earth's value is 9.8 meters per second squared. Mars. Mars is not as big as the planet Earth. It's not as massive. And so its gravitational acceleration, gravitational field strength, is only 3.7. So if we were to go to Mars, we would experience a little less than half as much gravity. So when you walk, you would feel a lot lighter. You would not weigh as much. Same mass, different gravity, therefore you experience a different weight. Venus, 8.9. Venus very much like Earth. We would probably not notice a huge difference there. Neptune, on the other hand, 11.0. It's a little bit more. So we might feel a little bit more heavy on the planet Neptune. Now, the law of gravitation. So Newton defines what gravity is and also the original calculation for it. Remember, he said that gravity is an attractive force between two objects that have mass separated by some distance, and that's what we have here. So he originally calculates that the force of gravity, again, always happens, force of gravity equals this gravitational constant, which we're not going to worry about what that is. Again, a constant is like pi. It's just some number that we multiply by. We have first object's mass multiplied by the second object's mass. And that's all being divided by the separation squared. So for us on planet Earth, the mass of the planet Earth is so huge that the numerator in this calculation becomes a very, very, very big number. Okay? Even when it's multiplied by our little tiny mass. And then in the denominator, we have the separation. Well, what would be the separation if we were stuck on the planet's surface? All things measure mass from their center of mass. So for the Earth, the center of mass is the Earth's core. So if we were to calculate the force of gravity acting on us using this equation, we need to know the radius of the Earth, how far we are from the center of the Earth. That's also a big number. Okay, and then when you square it, it becomes even bigger. But the net result is that when we calculate the force of gravity for an average size adult, this is going to be somewhere in the neighborhood of 800 to 1,000 newtons. Okay, so we can talk more about that calculation when I see you on Friday. If an object only has a gravity acting upon it, it's said to be in free fall. So when you have a skydiver, before their parachute opens up, they're falling down towards the planet's surface. They are in free fall. They only have gravity pulling them down. In the absence of air resistance, all objects would fall at that rate of 9.8 meters per second squared. That explains why when you drop a piece of paper next to a book, the paper doesn't fall as fast, because there's air resistance. But if you can get rid of that air resistance, like putting the piece of paper on top of the book so the book blocks the air, then they accelerate towards the Earth at the same time. But again, how is that possible? Well, you saw it in the Veritasium video. Drops a medicine ball and a basketball from the same height. They both hit the ground at the same time. One object is heavier than the other. The heavier object, such as the 100-kilogram object, all the time, 100 kilogram means more mass equals more inertia. And then you have the 10-kilogram mass, means less mass equals less inertia. Okay. Well, if we are to then use the fact that they accelerate at the same rate, we could calculate the force of gravity acting on each of these objects. We'd have 100 kilograms times 9.8 meters over second squared. That would be 980 newtons. Force of gravity acting on the 10-kilogram mass times 9.8 meters per second squared equals 98 newtons. Both objects are accelerating at the same rate, but they have different amounts of force on them. Different amounts of force for different amounts of mass, because they have different inertias. As he says in the video, the heavier object has greater resistance to changing its motion. So yes, gravity does pull down on heavier objects with more force, but even though it pulls down on them with more force, they still accelerate at the same rate as lighter things. Okay. So there's a different amount of gravitational force acting upon each object. Because of this, they ultimately have the same acceleration. Projectile motion, another consequence of gravity, is observed when we look at projectiles. So this would be something that you take it like a ball and you throw it through the air. Okay. So if we have two separate objects, if we take a ball and we toss it straight up, that ball will go up and then stop, and then it will come back down. Okay. Here the ball will go up and then come back down because of gravity. Gravity is the unbalanced force pulling down all the time. In the second scenario, we have an object that's going to be tossed to the side. And let's say it's like somewhere in outer space, so that there's no gravity acting on it. The motion of the ball would be to just travel in a straight line to the right, because according to Newton's first law, the baseball's inertia would cause it to travel in a straight line. An object in motion at a constant velocity will remain at constant velocity unless acted upon by an unbalanced force. So if we toss the ball straight up, it'll accelerate to a stop, and accelerate speeding up, coming back down because of gravity. If we had a ball that had no forces acting on it as it traveled through space, it would just continue to travel in a straight line. If we combine those two motions, though, what do we get? So let's say we have the ball, and as it goes up, it goes over a little bit. And then it goes up just a little bit more, and it goes over a little bit. And then a little bit up, because it's slowing down as it goes up, until eventually it reaches some peak. And then it will start to come back down again as it's moving over, and then it comes down a little bit more as it moves over, and it comes down more as it moves over, and then it comes down more as it moves over, and eventually the ball ends up at some other spot. If we take all of this and look at it together, we see that the ball actually travels in a bit of an arc. And this is what all projectiles do. If you've ever taken a football and thrown it, or a baseball or a softball, or you play volleyball and you've hit it and it flies up into the air, all projectiles follow the same kind of arc pattern. And this is because as the object moves to the side, gravity is pulling it back down. So all projectiles follow this kind of an arc pattern as they travel through the air. Now, on Earth, when we throw these things, they don't travel very far before they eventually hit the ground again. But what if you could take something and you could throw it so fast that this arc that we observe for the projectile matched the curvature of the Earth? Then what would that look like? Well, it would look like something that is orbiting.
Why do planets move in orbit? It's because of the force of gravity. Because of the sun's gravity, each planet would fall straight towards the sun if it was not moving sideways at high speed. Earth travels at 30 kilometers per second. This is exactly the right speed to keep it moving in a circle called an orbit. Smaller objects stay in orbit around a larger one because of the combination of its high speed and the force of gravity between them.
So, we would see something that went into orbit around the Earth, kind of like the Earth orbits around the sun. As it says in that short little clip there is a force of gravity between any two objects that have mass. So in this case, we're talking about the Earth and the sun. And so if the Earth was not moving through space, we would just go flying straight into the sun, and that would be bad. But we're also moving at a really high velocity away from the sun. And when we combine those two motions, we get this arc to where the planet is over here. Again, we have gravity pulling us in. We have our big velocity to the side. That causes us to arc to here. We have gravity going this way. We have velocity going this way. That causes us to arc to this point. Force of gravity going in. Velocity moving us away. And we end up traveling in this orbit around the sun. Just like if we were standing on the Earth and we took a ball and we threw it with enough force to get it moving really fast, the gravity is pulling it down, we could get it to orbit the Earth and have it come back around and hit us in the head. Okay. We see this with the moon. Granted, we didn't throw the moon, but the moon orbits around the Earth in the exact same way. There's a gravitational attraction between the two, so we're pulling the moon towards us, but the moon is moving at high speeds away. Okay. Big velocity moving away, gravity pulling us towards the Earth, and it goes into this orbit. So while the Earth is being pulled to the sun, it also moves perpendicular to it at enormous speeds. And an orbit is when there's an object that is in constant free fall. The only force that is acting on this object, as we defined earlier, when things are in free fall, only gravity pulling on the object. So gravity is always pulling it down. But if you're moving fast enough so that you never crash into what is attracting you, then you go into orbit. So you're in constant free fall. And this is what causes astronauts to feel weightless. Okay, so when you have the International Space Station and you see video of people bouncing around up there, quote unquote weightless, it's because the International Space Station is in constant free fall. It's orbiting the Earth. So the people inside the space station, like the space station, are always falling, always getting pulled towards the Earth, but they're moving sideways with really high velocity, so they never crash into the ground. So it creates this feeling of weightlessness, which can't be, because weightlessness would imply that there is no gravity. And there's always gravity. We're always going to be being attracted by some other large object. Okay. Like I said, on the International Space Station, we could do the calculations. If you want to see them, I could show it to you on Friday. the gravity at the International Space Station, which is, hundreds of thousands of miles away from the surface of the Earth, the gravitational pull is only about 15% less, so it's still quite high. Okay. There is no such thing as weightlessness, just constant free fall, which simulates that weightlessness. Anyways, that's it for today. I'm not going to give an assignment. We'll look at an assignment on Friday when we wrap up this unit on forces. Make sure you have all these notes. And please, if you have questions about anything that we talked about, you need to talk to me about it on Friday morning when we start class. Very important. Now, next week, we're going to be doing that Great Balloon Challenge, and that'll lead into the exam for this unit. And there's only a short amount of time left this school year. Let's finish up on a high note. So, anyways, make sure you get all the notes. Go back if you need to. Rewatch this video or the Veritasium video if you need to. And be ready with questions on Friday.